Okay, so let's use MATLAB to figure out how we can analyze this circuit using an arbitrary number of terms. We're going to start off with defining what our omega naught is of our input and creating a time vector. So we're interested in analyzing the first 10 seconds of the output. And really arbitrarily, I'll say we'll divide this up into 1,000 different sections of this first 10-second part that we're going to analyze. So this isn't 1,000 different harmonics. This is we're going to analyze the first 10 seconds at 1,000 different subpoints. Like if we're going to analyze it using a decent sized monitor with 1,000 pixels across it, this would be enough to have 1 pixel per part of the waveform. So this is plenty. We'll start off by handling the DC term. So for that, omega is 0, and our capital A sub 0 of our input waveforms, this is of our input waveform, we've already calculated to be 0. And so we don't really need to calculate what our system transfer response is, which is that at that particular omega, because we know we're going to multiply it by A naught. But just to be complete, maybe but just to be complete, you can use this form of an analysis program for your own circuits that have a completely different kind of input. I'll put this in. So our A naught prime term is going to be our A naught in term times our H evaluated at that frequency of 0, and that's going to be our output. So this is our output using only the DC value. Now we're going to start to calculate all those harmonics. Calculate the output from each harmonic input. So the first step is we're going to need to determine, we'll do this for 10 harmonics. So these are our little a sub n and little b sub n from the analysis we already did by hand. We'll construct the complex value c sub n and break that apart into a magnitude and an angle. So now we've got now at this point, after we've done this, we know that the corresponding nth term, we could represent it as having a magnitude of a sub n and at an angle of phi sub n. This particular frequency, our nth frequency, will be n times our fundamental frequency. Here's our transfer function evaluated at that frequency. And now we're going to find our output. So to find our output, we'll create this complex number again, which is really just the same as our c sub n, right? And we'll multiply it. This is our, maybe I should reverse directions to make it clear. This is our input. And this is our transfer function evaluated at that nth point. Maybe to make it still clear, I should say this is our nth value and our nth value of our transfer function. And so here's our output, Cn prime, and then the a sub n prime portion of it is the magnitude of this. The phi sub prime is the angle of this. And now our output is updated to include this harmonic reconstruction. And then we can plot the result. So let's save this and we will run it and take a look at what it looks like. So this is with 10 harmonics, and it already looks pretty close to a perfect triangle wave. You can see it's bent just a little bit to the right. It's curved just a little bit, but it looks like a triangle wave. This is a way that we can convert then a square wave into a triangle wave, if you want to, by putting it through this circuit that we built that's clearly a low-pass filter. You'll see it cuts down our signal a lot. That the original square wave went between -1 + 1. Now it's going only barely over 1/10 of that. But this is where the capacitor is charging up, and this is where the capacitor is discharging. But how do you know that 10 harmonics are good enough? Let's go back and convert it from 10 harmonics, and now we'll figure it out for 100 or 1,000 or 10,000. I mean, MATLAB does it all pretty much instantaneously. And here's our output with 10,000, and it really doesn't vary that much. It looks almost the same as when you computed it to 10, just 10 harmonics. That brings an interesting question. How close could we have gotten it with fewer harmonics? If you were concerned about how difficult it was to compute, how close would it be after only, say, 4 harmonics? And now you can see the accuracy suffers a little bit. You can see these bends in here, and that the top isn't quite as even. But we're certainly not going to add, it's certainly not going to change things much to go from 8 harmonics here, between 8 harmonics and between what it looks like with 10,000 harmonics. Remember, our original circuit looked like this. And we wanted to find this current. And I think it's clear for this particular configuration that if you had a really low frequency input, this capacitor looks like an open. So for low omegas, we get this. And for very high omegas, that capacitor looks like a short. And so for very high omegas, it's clear that our current will go down to 0. And so therefore we have a low pass filter. It passes low frequencies, this, in the limit, I think we said this was 2 and this is 1. So we said this would cut down our voltage by a factor of 3. And then as the frequency grows progressively higher, this denominator will get progressively greater and will cut down our output signal until eventually you get to 0. And this is exactly what we see in our MATLAB simulation, which kept the low frequencies and cut down the high frequencies, which means that the low pass filtering of a square wave is indeed this triangle wave.